So let us begin our today's session. So any questions on the previous class, what we discussed earlier? Say, do you have any queries on that? Anybody? Yes or no? I think I have given a small assignment that whenever we consider two ideals, if we have taken their intersection, it also become an ideal. And the second one is, if we talk of the union of ideals, then the union will be an ideal only when one set is the subset of the other. Have you tried for that? Any questions on that for anybody? Please tell. Right. So please ask your questions if you have any. Otherwise, let's start the new one. Or if you want to discuss the solution again, I will discuss the solution right now. Are you clear? Right. So let us stick with the other that the union of two ideals is an ideal if and only if one set is contained in the other. It is an if and only if part. Suppose we have taken two ideals I1 and I2. So as per the question pattern considered, so I1 union I2 is an ideal implies and implied by either I1 subset of I2 or I2 subset of I1. This is the thing we actually need to prove. So the simple thing is taking the converse. If you assume the converse, that is you say that either I1 is subset of I2 or I2 subset of I1. You can take either of the case. So if you take the first case that I1 is a subset of the other set, then if you consider the union, it is nothing but I2. Because in the two sets, I2 is the big one, so union is nothing but the bigger set I2. Since I2 is an ideal, these two are equal, therefore union is also an ideal. Accepted? All. Similarly, if you take the second case, here also union is nothing but the bigger set I1, hence union is an ideal. Therefore, in the converse part, the proof is very trivial. Now, if you consider the main part, so if you assume that the union is an ideal and we have to show that either this is subset of the second set or I2 is subset of I1, that we need to show, right? If everyone is clear with this logic, I take this part, the main part, to prove. I think similar kind of logic we applied while discussing with group theory. Union of two subgroups is a subgroup, if and only if one is contained in the other. Right? Is everyone comfortable with this? Other people? Fine. So while proving the main part, since there is no direct proof available for us, so we assume that the condition is false. So what is our assumption here? We assume that I1 is not a subset of I2 and I2 is not a subset of I1. So we are trying for the contrary way. So if you start the procedure, you will get a contradiction. Hence, our supposition must be wrong. Therefore, either I1 should be a subset of I2 or I2 should be a subset of I1. That we can confirm. Okay? Now, from this very assumption, we can say that there exists an element A which belongs to I1 and which does not belongs to I2 from this step. Similarly, there exists an element I2 such that that element will not be in I1. So you can imagine the diagram like this. This is I1 and this is I2. So A is an element exclusively in I1 and B is an element exclusively in I2. Now what happens? These two elements together belong to the union, the whole union. As per our supposition, union is an ideal, hence you can say that the difference between them belongs to the union. So what does it mean? I have two things, one value is A, another value is B, and I am taking the difference between them. The difference is a new value. That new value is belonging to the union because it is an ideal. So whenever you say that the element belongs to the union, it must belong to either of the sets. So the possible cases are either A minus B is in I1 or A minus B is in I2. Is it okay for all? Say. So if you say that A minus B in I2, so I2 contains two values. Since I2 is an ideal, simply applying closure law, you can say that A belongs to I2, which is wrong. Because we know that A will not be there. We can take the contrary way in either of the things. You can take the second condition or first condition, anything. So first condition is somewhat comfortable while applying the logic, because as and when I give a definition for you, we always think about the first condition, right? Rather than the second condition, the regular phenomena of mind. That's why you apply for that. Okay. So contradiction you can bring for either the first thing or second thing. So here our whole idea is, if you assume like this, you can do any kind of thing. You are not yet applying the condition of ideality here. So there is no need to bring contradiction for the ideal definition. You can bring any type of contradiction. Please understand that. Contradiction means you can bring any type of contradiction. There is no need to bring the contradiction for your supposition. Right. So see, either of the, you are bringing the contradiction for this assumption, not for the ideal condition. Please understand. We are bringing the contradiction for this thing, what you have taken initially. So to your initial values, you are bringing the contradiction, not for the ideality, because it is always ideal. You cannot bring a contradiction here. Okay, right. So if you say that a minus b belongs to this, taking the difference of these two, so whatever the thing you take that a minus b is belonging to either of the sets, you are getting a contradiction always. So our initial assumption must be wrong. Therefore, either I1 is subset of I2 or I2 is subset of I1. That we confirm. Okay? Fine. Right. So this is the solution of this thing. And the intersection part, I think everyone is comfortable in proving that. Can I take that one also? Or not necessary? Please tell. Fine. Now in today's concept, we will discuss some other new things. So one interesting thing while observing the ideals is we introduce the concept of principal ideal. What is meant by a principal ideal? Now, you take R as a commutative ring with unity. Let us take like this. R is a commutative ring with unity, and you fix an element in it. Now, you consider all possible multiples of this element. So you can simply write AR, or you can simply write it as RA, whatever it is. So you are taking all the multiples of it. So if you consider the set of multiples, it will become an ideal. So here you are simply considering the multiples of a single element. That is why we are calling it as the principal ideal. And since you are taking the multiples of the element A, we say that it is the principal ideal generated by A. So we simply denote with A with the symbols less than, greater than on either of the sides. Or you can simply write like this also, generated by A. Okay. So principal ideal is just like the concept of cyclic groups. You are simply taking all the multiples of an element for the whole group. In other words, the group is simply generated by one single element. Here also, principal ideal is nothing but you are taking only all possible multiples of an element. It satisfies the criteria of an ideal. Hence, we are saying that it is the principal ideal and it is generated by an element A. Okay. So please take a note of the definition. And always, whenever you take the case of commutative ring with unity, always the ring is a principal ideal. It is generated by the unity element 1. And if you simply take the 0 element, it is also principal ideal. It is generated by the value 0. So these two are always principal ideals. Please understand. The ring itself is always a principal ideal. The generator is nothing but 1. It is the multiplicative identity. And the single element 0 is always a principal ideal. It is generated by 0. Right? So you can find the other principal ideals also there. Okay? All of you. Now the interesting thing is, if you talk about principal ideal, the fundamental thing, if you consider the ring Z, the set of integers, the special quality of this ring is, it is a principal ideal ring. You also call it as PIR. So what is the specialty of this? You can find any ideal for Z. You take U as an ideal for Z, it is a principal ideal. So every ideal you can find a generator. So whatever the ideal you take in Z, it is nothing but a principal ideal. Since we know that it is an integral domain, so apart from writing principal ideal ring, we will write it as principal ideal domain. So in a short manner, we will write it as PID, principal ideal domain. So this technical term you have seen in the syllabus. What is a PID? You have a doubt? So this is the clarity for it. So whatever the ideal you calculate, it is a principal ideal generated by some value. If such type of ring or integral domain is there, we call it as a principal ideal ring or principal ideal domain. Okay? Are you clear? Please take a note of that. Then we discuss with the solution part. How we are going to prove that it is a principal ideal. Right. So here now, this is we want to show actually. Z plus dot is a principal ideal domain. So how we are going to show this? Now you can take any arbitrary ideal there. Because the ideal, what you have taken is 0, then it is principal. If you take the ring itself as an ideal, that is also principal. So, for every ring, there will be two ideals by default. These two we call them as trivial ideals. As and when you take the trivial ideals, they are by default principal ideals because it is generated by 0, it is generated by 1. So if you take any other ideal which is a proper ideal, say I have taken U here, so which is bigger than 0 and smaller than 1, here we need to show that it is principal. So we have to show that UV is generated by some number. Then we have to find what value is actually generating U, you have to know. Now the thing here is, since UV is not equal to 0, so it contains 0 value and non-zero values because it is bigger than 0. So if you consider the whole ring Z and if you have taken U in it, it contains non-zero values also. You take an element here, say A. Since you are talking about the integers, this value may be positive or negative. Accepted? A will be a positive value or A will be a negative value. Agree? In integers. So, while considering the set U, we simply look at that it may have the positive values, it may have the negative values. So, we simply bifurcate that as U plus and U minus, having the negative values and having the positive values. So, whenever you know a set of positive values, are you able to specify the smallest element in it or not? Say, are you able to specify the smallest element in it or not? Whenever I have given a set to you, it is possible. So if you have a doubt, there is a small result that well ordering principle. I think you have heard this name. Even though if you didn't know about this principle simply says that whenever you take a non-empty set of positive values, it always contains the least element. That is actually well ordering principle. Okay? It is beyond our content now, but you can keep it in mind. So well ordering principle is nothing but whenever you take a set of positive values, always you can say it contains the smallest element in it. Okay? Does it make sense? Now, in the positive values of U, you can fix the smallest element. Let us say it is B. The smallest in U plus is equal to B. So, our claim here is, I want to show that the ideal U is generated by the smallest element B. This is my claim. So now please observe what you have done so far. If you take the trivial ideals, they are by default principal, there is no need to prove. If you take an ideal which is a proper one, bigger than 0 and smaller than the ring, then for this you have to show it is a principal ideal. It means it should have a generator. So, since it is a non-zero ideal, it contains non-zero values. The values may be either positive or negative. So we simply bifurcate the set as set of positives and set of negatives, the inner separation there. So in the set of positive values, by well ordering principle, always you can fetch the smallest positive value, which is nothing but B. I am taking the name as B. Now here my claim is, I am going to say that this ideal is generated by this element B. So it means that whatever the value you take, that is nothing but a multiple of B. That we have to show actually. Okay? Are you fine? Now, you take any element in U. Now, actually, X is an integer, B is a positive integer. So, whenever you have taken integers, you can apply division algorithm. The very simple manner I will say, let me say, if you have taken number 5, you have taken number 12, you can simply go for the division. Say it cancels 2 times, 2 is the remainder. You can write 12 is equal to 2 into 5 plus 2. As dividend is equal to divisor into quotient plus remainder. Accepted? This we call it as the division algorithm. Euclid's division algorithm of numbers. So, X is a number, B is a number. I can apply division algorithm for these numbers. Because you are dealing with the integer set, the set of integers you are talking actually. All these are nothing but the integers. So you can write X is equal to BQ plus R. This is by division algorithm. So whenever you have written like this, the possibilities for R is either R is 0 or R must be less than B, because here B is the divisor. What could be the maximum remainder? You can take the remainders up to B. You cannot get B as a remainder because you are dividing with B. Now what happens? This is my expression as per division algorithm. Now, if I have shown that R is 0, then from this relation X is equal to BQ. So X is generated by B. X is a multiple of B. So every element X is a multiple of B. Therefore, our claim gets completed. Okay. Now the question is R 0 or not? That is the question. Are you getting the logic? Is R the remainder 0 or not? Now let us verify for that. Now let us check what happens if R is not equal to 0. If R is not equal to 0, then what happens? So from this relation, you can say X minus BQ is equal to R and 0 is less than, R is less than B. And for your understanding, I just want to draw a small picture for you. The picture will give you a good idea. It is very simple that this is the whole ring Z. In this we have taken an ideal U, so where it contains the smallest element B, and you have taken another element X. This is initially you have taken. Since U is an ideal, you can apply ideal properties there. Actually, whenever you write this type of relation, Q comma R basically integers. So what happens? Q is an element in Z, X is an element in U, B is an element in U. So by taking these two, BQ belongs to U. Since ideal second condition. In the definition of ideal, whenever you take one element in the set, one element in the ring, the product should belong to the ideal. Right? Again, you have taken two elements in the set, then the difference must belong to the same set. Ideal first condition. So, as we know, X minus BQ is nothing but R, therefore R belongs to U. Agree? Are you getting the idea or not? Yes or no? Right. Now you see, from the very choice of R, what is R here? It is a positive value and it is smaller than B, isn't it? Yes or no? From the very choice of B and R. So actually, by well ordering principle, you have chosen that B is the smallest element in U. It means that you cannot find the smallest element in U other than B. But here you are saying that R is belonging to U and R is smaller than B. This is a contradiction, right? So this contradiction is arrived because you have taken that R is not equal to 0. As you have taken that R is not equal to 0, you get a contradiction here. Contradiction to the smallest nature of B. Therefore, R equal to 0 is obvious. It is must. If R becomes 0, then X is nothing but BQ. So every element is a multiple of B. Therefore, UV is generated by B. So UV is a principal ideal. So in this way, whatever the ideal you consider, it is becoming principal. In other words, you can say that whatever the ideal you take, the smallest value is nothing but the generator for the ideal. That is the underlined idea there. The smallest value in the set is nothing but the generator of the ideal. How R belongs to U? See, x minus BQ is equal to R. I have taken that x minus BQ belongs to U, isn't it, from the diagram? So R belongs to U. Clear now. And R is less than B as per this choice. That's it. Therefore, every ideal is a principal ideal for Z. Therefore, Z is nothing but a principal ideal domain. Okay? You can say that the ring of integers is a principal ideal ring. Or you can say that the integral domain Z is a principal ideal domain. Okay? Please take a note of this. Then we discuss with other things. After noting, please inform. Right. Any questions or doubts for anybody over this whole result? Please tell to anyone. Fine. Now, as we talk about the fields, now I am given a field to you. Now the question is, how many ideals will exist for a field? So the answer for it is, for a field you have only two ideals. Those are nothing but the zero ideal called as null ideal and the field itself. That means that if you want to calculate the ideals of a field, you simply get only trivial ideals. A field will not have proper ideals. Okay? Are you clear now? A field has no proper ideals. Now let us prove it theoretically. So let us say you have taken a field F. And you take any non-zero ideal. Now my intention is, whatever the non-zero ideal you take for the field, it is becoming equal to F. Whatever the non-zero ideal you take, it is becoming equal to F. So what happens? Every ideal is becoming equal to F means F has only two ideals, 0 and F itself, isn't it? That is the idea to show this. And as you have taken UV is ideal of F, it is clear that U is a subset of F. In order to show this, it is our part to show F is subset of U. So from these two relations, you can conclude that U is equal to F, therefore F has no other ideals except 0 and itself. Okay? Is it clear for the whole strategy to all? Therefore, U and F both will become equal. So every radial of F is nothing but F itself. Now, as you have taken that it is a non-zero ideal, it contains non-zero elements. For a simple understanding, let us take the picture like this. This is the whole field F, this is U, and since it is a non-zero ideal, let us take a non-zero element here. So by default, A belongs to F. So this implies A belongs to F. Since F is a field, what is the fundamental property of field? Whenever you take a non-zero element, it contains the inverse. The very specialty of the field is it contains inverses for non-zero elements. So you can say that A inverse belongs to F. So you have A inverse here. Since UV is ideal, whenever you take one element in the set, one element in the ring, the product should belong to the set. Therefore, A into A inverse belongs to U as per ideal second condition. So whenever you multiply an element with its inverse, it is nothing but the identity 1. Therefore, we can say that 1 belongs to U. Okay? Any questions for anybody? Please tell. Right. Now, this very element, as you have taken that 1 belongs to U, it is enough to show that F is a subset of U. Because if you take any X in the field, since X is an element in the ring, 1 is an element in the ideal, the product belongs to U. As per ideal second condition. Therefore, F is a subset of U. Therefore, U is equal to F. That's it. Is it clear for you? So, apart from verifying that F is a subset of U, it is enough if we have shown that the multiplicative identity 1 belongs to U. Because as and when an ideal contains the element 1, automatically the whole ring will become subset to that ideal. That is the specialty of that element 1. See, as we have taken that 1 belongs to U, using ideal second condition, every element in the field is becoming to U. Therefore, F becomes subset of U. Therefore, U is equal to F satisfied. Therefore, the only ideals of the field are nothing but 0 and F itself. Okay? You just take a note of that. Is it clear? Any questions? Now, what can we say about the field after having this result with us? After having this result with us, what can we say about a field? Earlier, I have given one definition. A field has no proper ideals is absolutely correct. That we have actually proved. Prior to this, we have given a definition, right? What is the definition? I have discussed about the word PIR, isn't it? So, whenever the ring contains only principal ideals, that type of ring we call it as principal ideal. So, if you take the field F, it has exactly two ideals, 0 and the field itself. And these are nothing but principal ideals. It is generated by 0 and it is generated by 1. Therefore, all the ideals of the field are nothing but principal ideals. Therefore, the field is nothing but a principal ideal ring. Okay. Are you clear now? Every field is a principal ideal ring. If the same question is given to you, how you are going to prove? First, we prove that the field has only two ideals, 0 and itself. Second, we say that these two are principal ideals, hence the field is a principal ideal ring. That is the conclusion. So the beauty of abstract algebra is whenever you have a set of results with you, 1, 2, 3, 4, 5, so on, by combining the results, you can form a new result. That is the beauty of abstract algebra. Okay? Please take a note of that. Then we discuss the other concept. Shall I continue? Fine. Now, there is an interesting concept that maximal ideal, prime ideal. You take a note of these two definitions. Maximal ideal, prime ideal. These are very interesting topics and many questions are also asked in the previous year papers based on them. So, as and when you take an ideal, by observing a quality of it, we give the name that it is prime ideal and it is maximal ideal, right? So let us take the definition of prime ideal first. Now, you take the ring R and you consider as ideal which is not equal to R. Now we say that U is prime ideal if whenever A dot B belongs to U implies either A belongs to U or B belongs to U. This is the definition of the prime ideal. For diagrammatic view, you can say like this. So if you take an ideal U ring R, we say that it is a prime ideal that whenever you take any two elements in the ring, A and B, any two elements in the ring such that the product of the values will belong to U. So on multiplying A with B, the result will belong to you. Whenever this situation happens, automatically in the two elements, either the first one A will come to you or the second one B will come to you. This is the definition of a prime ideal. In other words, you can say that the product will belong to you only when one of the elements, at least one of the elements will belong to you. Okay? Clear? So please take a note of it. Then I discuss about maximal ideal, if you have known the definition of prime. And by default, for every ring, the null ideal is the prime ideal. Singleton 0 is prime ideal. It satisfies the condition by default. So singleton 0 is always a prime ideal. Now let us take the other definition, that what is meant by a maximal ideal. So you take M not equal to R is an ideal. We say that M is maximal if there exists no ideal of R which properly contains M. Which properly contains M. So whenever you take a ring R and M is an ideal which is not equal to R, then we say that M is maximal ideal if you cannot find any ideal which properly contains M. In other words, if you want to say a small picture on it, say this is the ring R, say this is the ideal M. So this type of situation will not arise. Suppose if you say that U is an ideal. So in this what happens? U is bigger than M and smaller than R. Accepted? So this type of situation will not happen if M is maximal. You cannot find an ideal which is bigger than M. Okay? I will give some examples for you. Let me say, so let us take the ring Z plus dot. Previously, we discussed that it is a principal ideal ring. So whatever the ideal you write, it is a principal ideal. So now you consider all the multiples of 6. So if you have taken that, it is nothing but so on. Minus 12, minus 6, 0, 6, 12, so on. Accepted? Now, is 6 a prime ideal? I will say it is not. Because you can find an ideal of Z which is bigger than 6. So the example is, suppose you have taken 3. So you can definitely say that 6 is a proper subset of 3, the ideal, because 6 is completely contained in 3 and 3 is definitely not equal to the whole ring Z. Accepted? So 6 is not a maximal ideal. Now the question is 3 maximal? That means, can you find any other ideal which is bigger than 3 and smaller than Z? Can you try? So please tell me the number. Which number the multiples has you have taken so that you can find an ideal which is bigger than 3 and smaller than z? Is it possible? That means you need to take a integer such that which contains all multiples of 3 and it is not equal to z. Is it possible for you? So we can say that 3 is maximal. 3 is maximal. Now let us take another examples also which gives a clear vision for you over this maximal ideals concept. Now if you take the same ring Z, so if you take the multiples of 8, take multiples of 4, take multiples of 2, now this is the hierarchy. Do you accept for it? The ideal 8 is properly contained in 4 and the ideal 4 properly contained in 2 and the ideal 2 properly contained in 1, the whole ring Z. Accepted all? So among which is the maximal ideal? Among the ideals 8, 4, 2, 1, which is the maximal ideal? Please understand, 1 is nothing but the ring. As we talk of maximal ideal, the ideal should not be equal to the ring. So 2 is the maximal ideal, right? So as one of our friends mentioned that as and when you observe that 2 is a prime number, so in this example 3 is a prime number. So the very result we can understand is whenever you take an ideal which is generated by a prime number, it is always maximal. And you can take the converse also. If you say that it is a maximal ideal of Z, automatically it must be generated by some prime number. Vice versa. So it is an interesting observation on the set of integers. Now let us go on to prove this. Shall we? Right. Now, theoretically, if you want to show that there is no ideal which is bigger than M and smaller than R, how can we prove theoretically? What could be the theoretical logic we go on to apply there? So, the theoretical logic is, from this very diagram, whenever you take the hierarchy like this, so whenever you have a pattern like this, then obviously we should be able to say that either M is equal to U or U is equal to R. Whenever a type of situation like this occurs, always it ends like either M is equal to U or U is equal to R. If you are able to say like this, it means that there is no ideal which is bigger than M and smaller than R. It indirectly implies the same thing. Accepted? That's why in order to prove that M is a maximal ideal, so we need to bring a situation that if M subset of U subset of R, then either U is becoming equal to M or U is becoming equal to R. So you cannot find an ideal which is bigger than M and smaller than R. Therefore, M is nothing but the maximal ideal of that ring. That we prove. The theoretical logic while doing the result is that. Okay. Now let us discuss on it. So what we are discussing now is the statement. Formally we write it as in the ring of integers, the ideal generated by prime number is maximal. That is the thing we have taken now. Please take a note of this and we will prove. After noting, please tell. Right? So let us take that. Let M is equal to generated by P. P is prime. Is an ideal of Z. And we know that Z is generated by 1. So to show that it is maximal, let us take any other ideal. So our claim is M is maximal. This is our claim. So for this, let U be any ideal of Z. Such that M subset of U subset of Z. As we know that Z plus dot is a principal ideal ring. So U is principal ideal. So let us take that U is generated by Q. So this is the basic hypothesis I have constructed as per the data given. Please take a note of that and ask if you have any questions on it. Q is any number. So by default we can say that Q is bigger than P or smaller than P. You cannot say. I have taken a set like this. It may be of anything. Here you need to understand one thing. Abstract algebra is concerned with not only numbers, you can take polynomials and matrices also. If you say that M containing all matrices, U containing all matrices, then you say that which matrix is bigger than which one? Say. So definitely you cannot say that Q greater than P or P less than Q. You cannot say like that. This theory is applicable for all, not only for numbers. So here in this case, we can say that Q is greater than P is your assumption. Please understand, it is your assumption. Maybe if P is equal to Q, there is also a possible case, right? Because in order to show that M is maximal, our intention is nothing but you have to show either M is equal to U or U is equal to Z. This is our intention. So if you say that Q is bigger than P, automatically you have to show that Q is equal to 1. That is our only choice, isn't it? U is equal to Z. So you cannot take the conclusion straight away. Now see what happens in the next step. So as per the hierarchy considered, this is the order you have. So every element here belongs to here and every element here will belong to this place. Since it is generated by P, P belongs to this value. Accepted? If I have said that the ideal is generated by 2, by default it contains the number 2. So P is an element in the ideal P. This is subset of this one. So you can say that P belongs to the ideal Q. In other words, P is a multiple of Q. So you can write P is equal to Q into some integer M. Accepted? Yes or no? As we have taken that P is a prime number, as we have taken that P is a prime number, whenever you have written a prime number as product of two values, two integer values, then definitely one value must be equal to 1, isn't it? So if you take 5 as a prime number, you can write 5 as 5 into 1 or 1 into 5. This is the only possibility for it. Say yes or no. If you talk of integers. Therefore, among the two values, either of them must be equal to 1. So, the possible cases are either Q is equal to 1 or M is equal to 1. The possible cases. So, if you say that Q is equal to 1, then generated by Q is equal to generated by 1, nothing but U is equal to Z. If you say that M is equal to 1, then P is equal to Q. So generated by P is equal to generated by Q, so M is equal to U. Now see, this logic is proved here. Did you observe? Therefore, M becomes the maximal ideal. Okay. So please take a note of it. After noting, please tell. So from this very observation, you can say that the converse part you can try. If you say that M is maximal, then it is generated by a prime number, that you can try. If you didn't get the solution, I will explain you in the next class. So here, for Z plus dot, we can take the conclusion that an ideal in Z is maximal if and only if it is generated by a prime number. That we need to understand. This is good result. While proving the high level problems in the next sessions, we can make use of this result. So at this step, you can take one more thing, that in the previous class we have taken the concept of quotient ring, right? So here we define the quotient ring as R by I, where R is a ring, I is any ideal of R, and we define that it contains all cosets x plus I such that x belongs to R. So here we are defining the cosets with respect to the operation plus addition of two cosets. So as we know, whenever you talk of a ring, always ring contains two operations, addition and multiplication. So whenever you write the quotient set, what are the operations taken on the quotient ring or the quotient set? So there, the plus is defined as whenever you take two cosets, we simply perform the operation like this. So the example for it is, if you take 2 plus I plus 3 plus I, it is nothing but 5 plus I. The addition of the values. Clear? And the multiplication is also done in the same way. So the dot value is given by x plus I dot y plus I is nothing but xy plus I. So the pattern of cosets you are getting here is, for every element in here, you are getting corresponding coset in R by I. If I take x here, x plus I is the coset here. If I take y in the ring R, y plus I is the coset in R by I. If I take z in R, z plus I is the coset in R by I. Similarly, if you take 0 in R, the corresponding coset is 0 plus I, nothing but I in R by I. So here we talk 0 as additive identity of elements. So here we call it as additive identity of cosets. So what does it mean? If you take 2 plus I, it is nothing but 2 plus I. Because as per the definition of cosets you consider, so 2 plus I is nothing but 2 plus I plus 0 plus I, nothing but 2 plus I. Okay, that is the actual meaning of it. Similarly, if you take the element 1 belongs to R, corresponding coset is 1 plus I, and we know that 1 is the unity element in the ring R. So 1 plus I is the unity coset in R by I. Okay, so there is an interesting thing here. So what is the thing we need to understand? 1 is unity in R. So 1 plus I is unity coset in R by I. It means that whenever you take a coset, by multiplying this 1 plus I, you will get the same coset. Because if you take that x plus I dot 1 plus I, as per the coset multiplication I defined earlier, it is x into 1 plus I, nothing but x plus I. So this acts as the unity element in R by I. Okay. In fact, you can say that R and R by I has very similar features. We can say that R by I is just like a mirror image of R. R is a ring, R by I is a ring. R is commutative, R by I is commutative. R has unity, R by I also has unity. Just like that. So, in order to define the nature of field, whether R by I is a field or not, whether R by I is an integral domain or not, it is mainly focused on the ideal what you have taken. It is mainly focused on the ideal what you have taken. So here, the interesting factor we need to take is, if the ideal is prime ideal, then R by I is integral domain. It is if and only if. If the ideal you have taken is maximal, then R by I is a field. It is also a very interesting result. So these two results are already given in the previous year papers, and in the next class we are going to discuss on them. Right? So if the ideal is a prime ideal, the quotient ring becomes integral domain. If the ideal is a maximal ideal, the quotient ring becomes a field. Before that, R and R by I has same properties. Ring, ring, commutative, commutative, unity, unity, likewise. So the nature of field and integral domain are mainly based on the ideal what you have chosen to form the quotient ring. Okay, all? Since these two will take a little lengthy procedure, so at this moment I want to stop our today's discussion, and in the next class we will meet. So that's all for everyone. Thanks for your cooperation and everything.